Yes. Hi, good afternoon, everyone. Welcome to the Sustainability Leads weekly webinar for today, August 11, 2021. And it's a great pleasure to have you all here with us today. My name is Watchareeya Kaveevivitchai from Chemical Engineering Department, National Cheng University, Taiwan. I will be the moderator for today's session. And the topic today is green energy and environmental sustainability. As we all know, an increasing demand for grid energy storage due to the advent of intermittently available renewable energy sources and the desire to avoid climate change have led to an exponential growth of research into alternative energy technology as well as sustainability environment. So in today's session, we would like to show how we as scientists can help contribute to such an important global issue. Today, we will have 4 brief talks. Myself would be the first speaker, followed by Ms. Pimonpan, Inthapat, and Mr. Surawit, Kijsermkul. They're both from Chemical Engineering Department, Mahidol University, Thailand. And the last speaker is my Ph.D. student, Ms. Lithium also from National University. And each speaker would have about 15 minutes with 12-minute presentation and 2-3 minutes for Q&A. And I will be informing the speaker when there is 1 minute left by using the chat box on the right-hand side. So my talk today will be on multi-electron redox chemistry for next-generation rechargeable batteries. As we all know, lithium-ion batteries are considered to be one of the best energy storage technologies for small electronic devices. They have relatively high operating voltage and energy density. They have good cycle life and rate capability. However, if we want to reduce pollutions by using electric cars or wind or solar energy, we're going to need large-scale energy storage system. And this will place great demands on next-generation lithium-ion batteries. We need to have higher energy and power density, better safety, longer cycle life, and the battery is supposed to be more environmentally friendly. And most importantly, the battery must be cheaper. And this will put a great challenge on the quest for new materials. So the lithium-ion batteries that we have today still too expensive with limited energy density. We still have limited lithium natural resource, and lithium still has safety issues. So the electrode materials that we now using in traditional lithium-ion batteries are transition metal-based inorganic intercalation compounds and graphite as cathode and anode. And if we take a closer look at these compounds, the traditional cathode materials, we can see that they all have different cell voltages, different capacities and energy density, as well as advantages and disadvantages. For example, for this most common cathode material, LiCoO2 with layer structure, it's expensive and toxic, and it has limited practical capacity. Now, if we take a look at this one, the olivine compound, LiFePO4, even though this compound is cheaper and is better for the environment, but it still has issue with limited lithium-ion conductivity. So over the years, there are a lot of efforts on the transition metal-based cathodes, such as LiCoO2 in particular, by doping, coating, and partial substitution of cobalt with nickel and manganese in order to optimize the performance of the commercially available lithium-ion batteries, and also to increase the practical capacity, which are now much lower than the theoretical value. However, further enhancement of energy density from these traditional materials is becoming more challenging, and it seems that inorganic materials have reached the critical limit in their performance. So most of the electron materials in the today lithium-ion batteries are based on transition metals such as cobalt and nickel, which are toxic. They are known to cause cancer, and overexposure to this metal may cause a lot of serious health issues. Now, availability is also another concern. For example, cobalt is rare. It can only be found 20 ppm in the Earth's crust, which makes it too expensive and the availability too limited for mass production. These drawbacks have not considerably affected consumers' electronic market, but they will definitely pose a significant problem in the large-scale energy storage application. So in order to address these issues, new materials that are abundant, inexpensive, and more environmentally friendly with higher energy density will need to be discovered. Now, organic compounds are considered to be more environmentally friendly. They compose of light, naturally abundant elements such as these without expensive toxic metals. They can be prepared directly from abundant renewable resources and easily synthesized from small molecules. And this can reduce the energy consumption and carbon dioxide release during mass production. Unlike materials with transition metals, which come from depletable mineral resources and require intensive mining, processing, and disposal. Organic compound can be designed and synthesized to contain various redox active functional groups. And due to this fascinating chemical and structural tunability, a large number of redox active sites may be incorporated, allowing multiple electron transfer, yielding high practical capacity. And the redox potential of the organic electrode material may be engineered at the molecular level by introducing the electron withdrawing or electron donating group in order to increase or decrease the redox potential. So organic compounds may be fine-tuned as both cathode and anode materials. Up till now, diverse structural types have been investigated as organic electrode materials, such as these conjugated polycarbonyl compound, conducting polymers, radical polymers, organosulfur derivative, and heteroaromatic compounds. However, in most organic electrodes, issues such as the low electronic conductivity and material dissolution in the typical organic electrolyte generally lead to capacity fading and low Coulombic efficiency. Several strategies have been used, such as polymerization and post-synthetic functionalization and salting. However, this strategy may result in an increase in the molecular weight as well as low energy density. Therefore, new structural design strategy toward the development of organic electrode materials capable of providing high energy density, high rate capability, and great stability are still needed. Now, one way to increase the energy density is to incorporate multiple redox centers to allow multi-electron transfer. And HAT compounds have emerged as promising organic cathode materials due to these several advantages. However, in most cases, only single HAT redox active functionality may be accessed. And more importantly, because of the small molecule-based material that will usually suffer from dissolution. So potentially by having additional redox active group through conjugation to the HAT core, we can improve the structural stability as well as the electrochemical performance. Now, inspired by a work published in Nature Energy, this compound 3Q with HAT core with 6 electron transfer. The compound 3Q can deliver pretty high capacity as well as good rate performance. So with this work, this inspires to further improve the performance. Okay, so in order to increase the number of functional groups, the redox active functional group, and also to facilitate supramolecular organization to enhance the cycling stability by using high extended structure, we have designed and synthesized a new compound called HATAQ with this structure. So comparing to the 3Q, we use this compound here as an intermediate. So you notice that this compound will now have 12 redox active sites capable of undergoing 12 electron transfer. And the molecule are packed together by using hydrogen bonding, okay, to form layer like this and stacked together in a similar fashion to graphite. And by introducing conjugated quinone to the structure, we found that the redox potential as well as energy density can be significantly increased. And we use EPR, we use XPS, as well as in situ Raman in order to understand the redox mechanism. And the characterization techniques confirm that both the CN group and CO group will participate in the redox reaction, having interaction with lithium ion. And we also have DFT calculation to locate or to identify the position where lithium will be inserted into the structure, such as this. And we confirm that the compound can really be inserted for up to 12 lithium. Now, comparing the performance to the previously reported work in the literature, we found that with this new structural design, we can achieve much higher initial capacity, and it can allow much better rate performance. Okay, and this work has been published recently this year in Advanced Energy Materials. Now, one of the strategies to alleviate this dissolution issue of organic materials is polymerization. And we have also extended our study to a family of porous polymeric materials. So the porous frameworks are expected to be capable of accommodating more gas ions via multi-electron redox reaction, thus providing high capacity. The alignment of the p orbital to the layer organic building unit could also be varied to fine-tune the electronic transport in the structure. And so the porous organic polymer, POP, condensed from the NDI and TFP, has been prepared in our group and used as cathode materials for sodium-ion batteries. Now, the electrochemical performance of the polymer has been further optimized by exfoliation. And the specific capacity, we also use AFM as well as BET to confirm the exfoliation process. And the specific capacity, almost as high as the theoretical value, can be obtained from the exfoliated compound with rate capability and capacity retention far superior to the non-exfoliated one, despite the low surface area of the exfoliated material. And these results are in contrast to the perception that crystalline framework with large uniform pores and high surface area are needed as host material for large gas ions, such as sodium ions. Now, by using exfoliation technique to reduce the stacking thickness and also to make the redox active site more accessible to sodium, superior properties can be achieved. And with this, I'd like to thank you for your attention, and I will be happy to answer any question. Is there any question from the audience? So the work that I presented here today, because we have limited time, so I selected two projects to show you that we have made some effort into reducing the amount of toxic transition metal with ultimate goal of developing electrode that are safe and totally free of toxic metals. And with this, we believe that materials that are naturally abundant, low cost, environmentally friendly will be very promising for next generation rechargeable batteries. So if there is no question, then I would like to move on to our next speaker, because looks like I'm trying to keep the schedule here. Okay, so let's move on to the next speaker, Ms. Pimonpan Inthapat. And let me stop sharing. Yes, so Ms. Inthapat, topic will be a comparative study on field properties and pyrolysis behavior of torrefied biomass pellets where pelletization before and after torrefaction processes. Okay, so this is another aspect of work that we have. Okay, all right, so please, Ms. Inthapat.
Hello everyone, my name is Pimonpan Inthapat and belong to Assistant Professor Dr. Kaveevivitchai. And today I will present on my topic of a comparative study on field property and pyrolysis behavior of torrefied biomass pellet via pelletization before and after torrefaction process. The biomass is alternative energy source from in Thailand. Then I need to use the agricultural and forestry as product biomass to use in my research, because this resource can use to produce heat and power generation via chemical conversion and can reduce using non-renewable energy to reduce the environmental issue of global warming and climate change. Moreover, these resources have advantage of recycle, abundant, carbon neutral, and reduce directly burning in Thai. But using biomass directly has some disadvantage of low density and high oxygen content that lead to the fuel efficiency when using in thermochemical conversion. So that biomass is essentially the suitable pretreatment process to solution these problems. The pretreatment by physical of pelletization and the thermal pretreatment by torrefaction process, because pelletization can increase the density and torrefaction can increase carbon content, energy density, and heating value. Moreover, it can reduce moisture and oxygen per carbon ratio. So the combined both of two pretreatment process is suitable to produce high quality. Nowadays, we have two main pathways to combine pelletization and torrefaction. The first way is pelletization after torrefaction, and the second way is pelletization before torrefaction. From the previous study that showed in this slide, show the research has study on the energy consumption, mass and energy balance, and quality property, and the parasitic characteristic. But they use only woody waste or agricultural residue to study in this property. Then it still lack for the information. So my study necessary to use two woody biomass from Louisiana and rubberwood, and two agricultural residue from livestock and sugarcane leaf. After that, I will guiding or biomass to lower the 1 centimeter before experiment. Then our biomass will take to pigment process. The first process is pelletization after purification process, or called PAG. This step, the biomass will purify under 3 different temperatures of 260, 280, and 300 degrees Celsius for 5 minutes. And then they take to pelletization by mixing water and contrast binder. For the second is pelletization before purification. For this process, I will use pelletization first and take to purification process. Then the goal of my research is to produce high quality solid fuel with high percentage of peak carbon content and high heating value by combine both process of pelletization and purification. Moreover, the field property of purified biomass pellet will compare with raw and lignite coal to control and understand the purified biomass pellet. For the biomass pellet, raw biomass pellet, it shows after pelletization, it can increase bound density, but it still have high volatile nature and low carbon content and high heating value. So my objective study, the first is to compare field property of purified biomass pellet via pelletization after purification and pelletization before purification under various purification temperature. And the second objective is to comparatively investigate reaction behavior of combustion for their product. And this slide shows the result of peak carbon for purified biomass pellet. You can see from this slide, it shows peak carbon can increase after with increasing purification temperature because the percentage of volatile matter in purified biomass decrease, then leading to increased peak carbon in purified biomass pellet. But when compared between PAT and PBT product, it shows PBT purified pellet had higher peak carbon than those of PAT purified pellet. And this slide shows the carbon content by analysis. That analysis by CSN analyzer, we can show carbon content has increased with increasing purification temperature, and also had the PBT purified pellet had also higher carbon content, similar trend with peak carbon that I already showed, because it has the occur of high dehydration reaction after purification process. And this slide shows the hydrogen per carbon and oxygen per carbon ratio for purified biomass pellet. It has shown the hydrogen per carbon and oxygen per carbon ratio decrease with increasing purification temperature because it has the occurred dehydration phenomena. Then led to the property of purified biomass totally or even better than lignite coal. Especially purified biomass pellet that show is the best product for all biomass. On that ratio can increase the high heating value because it can increase carbon content and decrease oxygen and hydrogen content in purified biomass pellet. So purified biomass pellet of high heating value for purified biomass pellet also had increased. From this slide show the increasing of high heating value with increasing temperature, especially purified pellet at 300 degrees Celsius is the best product to to produce. And the PVT 45 pellet also had the higher heating value than PAT 45 pellet. Then I used 45 biomass pellet at 300 degrees Celsius from of biomass to study in the combustion behavior because they have the high potential than other products. This slide shows the TGA and DTG curve from the DTG analyzer under air atmosphere. This slide shows the woody from rubber wood have the deeper peak than agricultural because it had the lower volatile nature than agricultural, and this curve show the DTG peak. It show the two main peak for combustion. The first peak is the volatile combustion, and the second peak is the char combustion. You can see in this slide, the PVT 45 pellet had the higher peak char combustion peak than those of PAT and raw pellet. After that, from the data from this curve used to the calculate by this equation to get the combustion index. The combustion index is mean the combustion performance reactivity. If the product had high combustion index, is mean better. But from this study, raw biomass pellet has high combustion index because it has high volatile nature than 45 biomass pellet. So raw it has higher combustion index, but PAT and PBT 45 pellets still have high potential than raw biomass pellet, even though they have low combustion index, because 45 biomass pellet had the high heating value, high oxygen, high carbon content, then it still have high potential than raw. But from my study found the PBT 45 pellet has more efficient than PAT 45 pellet. This is my conclusion from the different process sequence of PAT and PBT that used for biomass type from woody and agricultural residue by using 260, 280, and 300 degrees Celsius for 5 minutes. Is found the PBT 45 pellet at 300 degrees Celsius derived from agricultural residue at higher peak carbon content and high heating value, and the lower of hydrogen per carbon and oxygen per carbon ratio than those of woody biomass. And for the combustion behavior, it also show PBT 35 pellet higher potential than those of PAT 35 pellet. And this my reference in this slide, and this my acknowledgement. I really thank for Dr. Assistant Professor Dr. Wirawutchai that he helped me everything and support me everything. That I really thank you for him. Thank you for your kind attention.
Okay, thank you so much, Ms. Inthapat. Now we have 2 minutes for questions. Do we have any questions from the audience?
Professor,
No.
can you read from the chat box?
Yes.
Yeah.
Yes. Oh, yes. Okay. Okay, so we have one question that I read from the chat box. I don't know if Pimonpan, can you see this?
I see. Oh,
There are two questions.
the question. Polymer or this formattation or
Wait. Yeah, actually, it's just one question for you. Actually, is it? I think those two are supposed to be from me, right?
yes.
Okay. Now, well, while we wait for some, I have one question myself. So you're doing the torrefaction process, right? And
Yeah.
the purpose is to remove the volatile component from the material. So what are the volatile components besides water?
Sorry, Professor, can you repeat again?
For the torrefaction process,
Yeah.
what is the purpose of this process?
I need to review the oxygen and hydrogen because that can lead because it can reduce the high heating value also increase, then the property is will increase. Yeah.
Oh, okay.
But I need to improve the high heating value for the product.
Okay. So now, and then you have one conclusion that said when the temperature is higher, then you will have higher carbon content,
Yes.
right? So I wonder, so for the sample that has low carbon content, what are the other components inside?
For the carbon.
Besides carbon, what else do you have?
For another packet that another carbon content, right?
Yes.
For me, I need to focus peak carbon. Also focus on the peak carbon and high heating value.
Okay. Mm.
And moreover, I need to study on the another property, but it's still in the process because I need to know more what the base for PAT or PET in another way, but it still has in the process.
Oh. Okay. Well, very interesting project. Okay. Now, thank you. So because of the time limitation, now I'd like to move on to our third speaker, Mr. Surawit Kijsermkul from Chemical Engineering Department, Mahidol University, Thailand. So whenever you're ready, you can share your screen. Thank you. We cannot hear you. You have to turn on microphone.
Good afternoon. My name is Surawit Kijsermkul from Chemical Engineering, Mahidol University, Thailand. My advisor is Dr. Vanida Kuamon-Patana. Today, I would like to talk about my work, co-pyrolysis of glycerol with palm empty footprint using hybrid catalyst from zeolite derived from kaolin and activated carbon. Lignocellulosic has been the most sustainable and renewable source of organic hydrocarbon alternative to petroleum for fuel and chemical production with carbon neutral and net zero carbon dioxide emission. In Thailand, palm empty food run is main palm oil biomass residue, around 32% of by 32% by mass of palm oil feed were produced, but only 46% by mass of palm empty food run can be used. In my study, palm empty food run and glycerol were used to produce bio-based chemical by co-pyrolysis in fixed-bed reactor. By the catalyst is activated carbon and zeolite composite material, or we call hybrid catalyst, was synthesized from hydrothermal process. In combine to take advantage of their different characteristics by hydrothermal. Aim of study to gain an extensive for the co-pyrolysis of palm empty food run, the waste from palm oil industry and glycerol, the byproduct from biodiesel production to produce value-added chemical. To synthesize the hybrid catalyst from activated carbon and kaolin by hydrothermal process used for co-pyrolysis process. To investigate the influence of using hybrid catalyst for co-pyrolysis of palm empty food run and glycerol in fixed-bed reactor to produce value-added chemical. The mechanism of convert the lignocellulosic biomass. Cellulose is contained in dry wood about 40 to 50% by weight. The main product from pyrolysis of cellulose are acid, alcohol, androus sugar, char, and gas. For hemicellulose, is usually for 25 to 35% by weight in biomass. Ceylan was chosen as a model component to predict the hemicellulose. The pyrolysis of Ceylan produce acid, aldehyde, and ketone, carbon dioxide, carbon monoxide, methane, and hydrogen, acetic acid, and furfural. For lignin is contained in biomass about 16 to 25%. During pyrolysis, the cleavage of ether and carbon bond in lignin that will produce phenol and char forming. For pyrolysis of glycerol, as you can see in the figure 4, the acetal was formed by dehydration reaction, and there are two main route exits in upgrading of glycerol to aromatic over the catalyst. One is aldol condensation and route 2 is decarbonylation or hydrodeoxygenation or deoxygenation. It can produce aromatic. This is previous studies about catalytic pyrolysis of lignocellulosic biomass using activated carbon as catalyst. The result showed the product of bio oil has a high phenol content around 50%. And this is a study for conversion of glycerol by using zeolite based catalyst. The product show the high aromatic in bio oil product. For the result methodology, first I prepare activated carbon from carbonization of palm kernel shell in fixed bed reactor and then activate by physical activation using superheat steam to produce activated carbon, and then prepare metakaolin from kaolin by calcine in muffled furnace at 600 degrees Celsius to produce metakaolin, and then prepare hybrid catalyst by mix activated carbon and metakaolin as various ratio, and then mix with 3 molar sodium hydroxide solution, and then heat at 100 degrees Celsius for 20 hours at autogenous pressure and watch until the pH was around 7. And for copyrolysis process, the copyrolysis process in fixed bed reactor, this is a fixed bed reactor that we use. The copyrolysis of palm empty food barn and glycerol ratio of 1:1 in the fixed bed reactor. The 30 grams of the mixture of palm empty food barn and glycerol were used at the temperature at 500 degrees Celsius for 60 minutes. The nitrogen for as 200 milliliters per minute using the catalyst 3 grams or 10% by weight. The catalytic we compare the activated carbon and the hybrid catalyst with SZFM5 catalyst and compare with non-catalytic reaction or thermal condition. For the catalytic catalyzation, the XRD result show that the peak at 12.34 degrees show the after activated thermal activation of kaolin, the XRD pattern of metakaolin exhibit the change of this apparent of peak of kaolinite. This is a peak of kaolinite, and the quantitative analysis of kaolin and metakaolin is shown in the table. The result confirm that the kaolinite phase was disappear. And after hydrothermal treatment, the various ratio of activated carbon and metakaolin as 3 to 1, 1 to 1, and 1 to 3. The metakaolin was react with 3 molar of sodium hydroxide solution. The XD pattern show the peak of 12.4 is a peak of sodium A zeolite. It indicates that during the hydrothermal reaction, the crystalline phase of metakaolin was changed and transformed into sodium aminosilicate hydrate or sodium A zeolite. And for SEM micrograph, reveal that activated carbon has a glossy but porous phase with a variety of pore size owing to the activation with superheat steam at high temperature, and zeolitic product obtained after hydrothermal reaction of metakaolin show the alignment of the surface structure comprise small spherical particle. And for micrograph in figure 11 show the represent of the effect difference of activated carbon to metakaolin, confirm that the effective distribution of the small zeolitic particle on activated carbon surface. For the copyrolysis using hybrid catalyst, the yield of liquid show that the activated carbon show the highest percent of liquid product, and the hybrid catalyst using at ratio 1 to 3 promote the highest yield compared to other hybrid catalyst. And the chemical composition of the liquid product are characterized by gas chromatography mass spectral shown in the table. The result indicate that the liquid product consists of interesting chemicals such as acetic acid, acetal, pyridine, furfural, 2-cyclopentane and their derivative, and phenolic compound. For using the hybrid catalyst, ratio 1 to 3 show that the product has a high total chemical composition compared to other conditions, approximately 49.8% area. Conclusion: hybrid catalyst ratio of activated carbon to metakaolin at 1 to 3 promote the higher liquid yield compared with hybrid catalyst, and the chemical composition of liquid product consists of acetic acid, acetal, pyridine, furfural, 2-cyclopentane compound, and phenolic compound. Activated hybrid catalyst from activated carbon and metakaolin ratio 1:3 promote the high total chemical composition of the chemical. Thank you.
Okay, thank you so much. Surawit, I think you have one question from the audience.
Okay, let me see.
Yes, so it said the waste of this process could be reused as the ingredient, I believe, input ingredient for the next process or not?
The waste?
Yeah, the waste from your process could be reused or not.
You mean biochar from the co-parasite, right? And I'm not sure, but if is biochar, it can be used for the fuel. We can use biochar for produce to activated carbon or something.
Oh, okay.
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 Thank you.
Okay, because we're running a little behind schedule. So let's move on to our last speaker. My PhD student, Lina. Okay, so she also from NCKU Taiwan. Don't forget to turn on your microphone.
Okay, can you hear me?
Yes.
Okay. Hello everyone, my name is Lina. I'm from National Cheng University. Today I'm going to talk about multi-electron redox active material for high-performance aqueous ion batteries. I'll start by giving you an introduction about lithium-ion batteries. It is the most successful in the commercial battery markets, but still facing through some drawbacks such as high cost, limited resources, or safety issues, have brought growing concerns for further use in large-scale applications. Besides, aqueous electrolytes provide several advantages, such as higher ionic conductivity, lower cost, and non-flammability. Furthermore, zinc metal is an ideal anode for aqueous ion batteries due to the cheap price with high abundance, high stability in water, high safety, and low toxicity. Therefore, aqueous ion batteries are highly promising for alternative systems. As my professor has mentioned, this is our motivations to make the HATAQ. We expected to get high capacity, high conductivity, and stability. HATAQ has recently published in Advanced Energy Material Journal. To further develop, aqueous ion battery was considered as the next candidate. Now let's take a look at the electrochemical behavior of HATAQ in aqueous ion batteries. HATAQ exhibits the high capacity as well as the stable capacity retentions. As you can see, the capacity of around 500 milliamps per gram was obtained at the current density of 50 milliamps per gram, which is very close to the theoretical capacity of HATAQ. And the current density was also increased to 20 amps per gram with a stable retention for 1,000 cycles. A stable capacity was also obtained for 100 cycles, reaching a high Coulombic efficiencies of nearly 100%. HATAQ was also shown the highly reversible rate capability. The capacity is close to initial capacity when resuming the current density at 50 milliamps per gram. Now let's move to the mechanistic study. In aqueous electrolyte, the dissociations of water will form proton and hydroxides. According to the literature, proton may insert into carbonyl and amine group of HATAQ with a complicated mechanism, and this will be proved by combining the electrochemical performance and the in situ characterization. To determine the proton insertion, the typical non-aqueous electrolyte was used. These results demonstrate a much lower capacity with the absence of proton. For comparison, we add water into the non-aqueous electrolyte. The capacity from this mixed solvent electrolytes is significantly increased, which may occur the insertions of proton together with zinc. Interestingly, when the pure water used as the solvent to prepare the aqueous electrolyte, the obtained capacity is close to that of mixed solvent electrolyte. The change in the carbonyl and amine groups was first confirmed by using FTIR spectra. There are two strong peaks belong to carbonyl and amine groups. During discharge, the intensity of these two peaks decreased, indicating the reductions of the two redox active groups. During charge, the intensity of these two peaks increased to the initial level, suggesting the oxidations of the redox active groups. As I have mentioned earlier, a large amount of hydroxides is also formed together with proton. Considering other reports, the formations of the new product on electrode surface can be identified as the zinc hydroxide sulfate with a flag-like morphology as shown in SEM images. Besides, the strong signals from in situ XRD is an important evidence for the formations of the byproduct. During the discharge process, the peaks from the byproduct gradually become stronger, while the byproduct peaks appear to be much weaker at the end of charge, implying the reversible structural evolutions of HATAQ. To unravel the reactions mechanism, in situ XPS was examined. At the end of discharge, the new signal appeared, indicating the insertions of ionic charge carriers, and these signals are decreased the intensity at the end of charge, suggesting the extractions of the ionic charge carriers. The mechanistic study of HATAQ was further carried out using GITT and EIS. In GITT, the pulse signal is gradually changed during the discharge process, which can be attributed to ion diffusions of proton and zinc ion. Our result is different from previous report, showing in this figure, where a certain voltage change indicated the two-step insertions of proton and zinc ion insertion into the manganese oxide material. Here is the EIS results. During discharge process, the manganese oxide material was reported with two-step insertion of proton and zinc ion with significant difference resistance. In our case, the cell resistance appeared to be gradually smaller. This most likely means that the more zinc and proton ion interaction with HATAQ, the more conductive the structure becomes. This analysis provides strong evidence for co-insertion into the HATAQ cathode material, which is very important in mechanistic study. And this table is comparing to the literature. HATAQ has shown the highest capacity at the both high and low current density. Besides, it's also capable of very high current density at 20 amp/grams. Therefore, HATAQ material is considered to have the best electrochemical performance among HAT-based material. Finally, this work illustrates the molecular designs on organic electrode This material provides the excellent electrochemical performance, and the complicated mechanism was confirmed related to the proton and zinc ion co-insertion. With that, I would like to thank you for your attention.
Okay, thank you so much, Lina. I believe that we have some more questions in the chat box. There is one that I can see for Pimonpan. Okay, but because we a little behind our time schedule here, so I would like to propose that we answer the questions after our group photo together. Okay. So for those of you who have questions, you may stay in the meeting room a bit longer, and then we can reply. We can give some answer to the questions. Now, before we end our session today, we've been requested to have group photo. And so we would like to ask all of our audience to turn on the camera so that we can see your faces. So please, if possible, could you please turn on your camera and then we can have a quick screenshot together. Yes, thank you. So maybe we'll give it a minute or so. Okay, so if it's possible, please turn on your camera. And I think Dr. Huynh will, okay.
Yeah.
Yes.
Okay, when I counting 1, 2, 3, I got the picture. Okay. Okay, let's start. 1, 2, 3. Okay, one more time, please. 1, 2, 3. Okay, thank you so much.
Okay, thank you so much. So I think our webinar today will officially end here. And then for those of you who would like to stay a bit longer for questions, for Q&A session, then please go ahead and do so. Okay, thank you so much, everyone. And thank you, Pimonpan and Surawit. ขอบคุณนะคะที่อุตส่าห์มาพูดให้ อาจารย์ไม่ได้มาฟังในนี้ใช่ไหม เพราะฉะนั้นเราทำอะไรก็ได้อาจารย์ไม่รู้ใช่ไหม
อาจารย์น่าจะดูทีหลังค่ะ
ค่ะ มีคำถาม That's one question for Pimonpan at 2:34 p.m. Maybe you can try to answer this.
Sorry, Professor, which question that
It says from Lam Ha to everyone at 2:34 p.m. The question is, what are the factors that affect reduction reaction of carbon dioxide to fuel, methane, and chemical feedstock? What is the efficiency of this reaction? It came at 2:34 p.m., so I believe that one should be for you, right?
really, but for my thesis, we didn't focus on the carbon dioxide and chemical system.
Okay, so perhaps actually, Lam Ha is still in the meeting room, so perhaps okay, well, let's wait a few minutes and see. And I think is there one for me? Okay, so there's the first question at 2:18 asking what is the advantage of coordination polymers over traditional materials? So basically, it's the ability to fine tune the properties we want. For example, if we want to have higher specific capacity, then we can add more redox active functional groups inside, or we can use different functional group to adjust the voltage of your battery. That also can be done. So this is something that we can really do with traditional inorganic based materials. And another question is that if the project is successful, will it be difficult to apply in practice in large scale production? Well, right now, this project is still at the infancy stage, I have to say. So there are some indication that it could be done in large scale, okay? But it's gonna take some time before we can reach there. Okay, and I think that's it for me. Do we have any questions for Lina? Not that I can see so far. Okay, so I think, yeah, so that should be it for today.
Yeah, thank you, Professor.
Yes, so Dr. Huynh, are you in charge of all the webinars for this semester or for the whole series?
No, some of our webinar are hosted by Vietnam Hub, but the other is hosted by Malaysia Hub.
Oh, okay. Yes, because I have one more in November. I just wonder if I will see you. Okay. Okay.
Yeah.
So
Thank
let's
you
wait
so
and
much,
see.
Professor.
Yes, thank you so much.
Yeah, sorry, Professor. In the beginning, I just told that just waiting in 5 minutes because this time my internet would be lag. It's not clearly, so I just stopped you. Yeah.
Oh, no problem. No problem. Okay.
Yeah.
Yes, thank you so much, everyone.
Yeah. Have a nice day.
Yes, you too.
Yeah.
Okay.
Thank you. Bye bye.
ค่ะ สวัสดีค่ะ